Good morning, professors. We are from Chuen Public Ho Chi Minh Memorial College. Today, we are going to share our findings on rock, paper, scissors. Our report consists of two main parts. Firstly, we would like to find the expected values of rounds for n players to terminate, and then find the best way to optimize a rock, paper, scissors tournament in the second part. Let's start from the probabilities. There are two ways to find the number of non-draw cases. And by that, we can further find the number of draw cases. Now we let a function Pnk to find the probabilities of both cases and get these two equations. With these functions, we are able to find the probabilities for n players terminates in R rounds. Considering a two-players game, the table shows the possible rounds with its corresponding probabilities from 1 to 4 rounds. We then present the rounds in matrix form, as we would like to generate it as an array by a subprogram. The general matrix set would look like this. Then we use another subprogram finding the probabilities by this function. And now we are able to find the expected rounds En, and we have this definition for En. Originally, we find En by the summation of each number of rounds times the corresponding probabilities, and use a computer program to execute the results. Unfortunately, the program is too slow and inaccurate. So we switched to use a new method. With this method, En can be easily computed. Below are the findings we got after establishing the new method. As there is always infinite number of rounds, we firstly omit all the draw cases to limit the rounds. By this, E2 and E3 can be calculated by summation. As the expressions are too complicated, we introduced two new functions to replace the corresponding parts, although they have no actual meanings. With the help of functions, E2 and E3 are simplified as follows. Look at the expression in the green boxes. We define a function fx to present them, and find that fx is always 1. And this can be proved by contradiction. For details, please refer to the report. With the simplified expression, we find that En depends on E2, E3 up to En-1. But why? Looking at the rounds of a 5-players game, we can see that some parts of the rounds of 5-players game as that of 2, 3, and 4-players game. We call this the recurrence property of rock, paper, scissors. Looking into E4, we can replace the expression in color boxes with E2 and E3. As there is always an recurrence property, no matter how large n is, we can generalize the equation for En. And it is now independent from probabilities after E2, so it can be computed much faster. One of our teammates then wrote a program using this method. Afterwards, we plot a graph of ratio of En+1 to En, and find it tends to 1.5. Although we cannot prove it very well mathematically, we observe that the second part of the function is not comparable when n is large. With the expected rounds, we are able then find the best grouping method to optimize a rock, paper, scissors tournament. So here comes the second part of our report. We all know the rounds needed increase rapidly when the number of players increases. So we would like to divide them into groups to shorten the total time taken. For example, if there is 5 players, one of the grouping is shown like this. As we assume all groups in the same stage play concurrently, only the largest En in each stage will be added. In this example, it takes totally 4.5 rounds. By trial and error, we found the least total expected round Tn from n equals 3 to 27. Through this process, we generalized two grouping rules. For example, if there are 11 players, they are firstly divided into groups of 3 by rule 1, where the last group may contain less than 3 players. As there are 4 players remaining after stage 1, we divide them into groups of 2 according to rule 2. From the formulas, we found that the least total expected rounds for 3 in a group is the least. It shows that dividing into groups of 3 is the best, basically. We have already found the approximate value of Tn. But if we would like to have accurate results, we have to define all cases into 3 categories, which have different values of expected rounds in the last 2 stages. Then, we successfully found the boundaries of each category, presenting them using equations. And this allows us to find a category that certain n belongs to. For example, when n equals to 295, it belongs to the first category. With known category, n can be corrected as follows. Each category has different formula. In our report, we assume all groups in the same stages place concurrently. But what if they play sequentially, which means no groups would play at the same time? We find that group of 5 is the best case in this scenario. If anyone is interested, they may further investigate. All in all, there are total 3 main findings. The first one is the general equation of En, and the second one is the ratio of En plus 1 to En, and we find that it will tend to 1.5. And the last one is the best grouping method, which is grouping by 3, and the general equation of Tn. What have we done in this report can be applied to some other games, given that the rules are similar. For instance, game with 3 elements, almost the same of rock, paper, scissors. The logic behind may even be applied to Chinese 五行. And there is really such a game in reality. Here's an example for Chinese web-based game Mole Manor, using 3 elements to determine who's the winner. As there are still plenty of time, we would like to show you some interesting facts. If all of us in this conference room take part in a rock, paper, scissors game, how many rounds would it take? As there are total 20 people here, the expected round would be 1,142.9 rounds. And with the aid of computer program, we know that the time needed for 101 players game is remarkably long, even longer than the age of our planet. Given 2 more players, they may still be competing even if they start right after the birth of the universe. Yet, if we divide people into smaller groups of 3, the time needed will be greatly reduced. It takes only 47.25 rounds for a game, including all peoples in the world. And that's the end of our presentation. Hope you will find it interesting and inspiring. Thank you.